So hi, good afternoon. I was working on this for like the last week, but not all the time. So I'm not finished with this project, but went quite far already, and it's super fun, to be honest. It's really cool. Thanks to the help of Antonio, I'm really into it, and it's really great fun. But before I come to the interesting part, I have to bore you with some introduction. I guess it makes sense. So I'm working on this kind of camera experiment since a couple of years already. It's actually nearly end of life, this camera, but it's on the planet Mars for 20 years nearly, or actually, yeah, about 20 years. And the special thing about it is that it's a stereo camera. So it has several channels. So it's a push broom camera. You probably all know what that is. So there's only an image line and the Y. So this is the X direction of the image, and the Y direction is given by the flight speed, by the flight path. So, and usually you have only 1 or 3 for the colors or something channels. And this camera has 9 channels, so it can do 5 stereo channels at the same time. And stereo channels means that the same pixel is recorded from an angle, from different angles, and from all these views at different angles, we can calculate DTMs. So for every image, we have an adjacent DTM. So that's a big thing about this camera, and I think it's there are some airborne cameras on Earth, but despite this, it's quite unique. So, and yeah, that's a little bit the background. So you can see here the full coverage of planet Mars. So this is in grayscale, because the nadir channel is only in grayscale. And you can already see that it's not nice. It doesn't all fit together. It's got patches, black and white. It doesn't really match. So this is the coverage for the stereo, and so this was just an introduction for the camera. And the reason I can explain why it's not nice is that the orbit of the camera, the cameras, you know, from Earth, they are usually aligned with the sun. So that's called sun synchronous orbit. So it always covers the same, or the area it covers is always at the same sun angle, and that makes it easy for people to process it and to connect all these images together to a big mosaic, because that's how you are used to see the data on Google Maps, for example, to have it in mosaics. And actually, this mosaic creation stuff is what I'm into. And here you can see a mosaic. Now it's the real camera in more or less full resolution camera data. This is a mosaic of Valles Marineris. It's particularly bad, let's say, because it has a high topography. And here you can already see very well the problems we have with that. These images are perfectly aligned, and they are perfectly matched already with a big fuss of photometric routines. So usually it looks already much worse. So this is already a very good representation, but there's something we cannot really change, and this is the sun illumination at the time when the image was taken. You can see that this image, the sun came from here, and the sun came from there, and yeah, this is something you usually don't observe from other imagery, because they are, as I said, the orbit is sun synchronous. And my research idea was to create. So now this is from another area where we do these block mosaics, and here the case is not that bad, but it's also problematic, because what we then do, I mean, nowadays there are cameras.
Hey, Sebastian.
Yeah.
Question. So this was aligned manually. Is that what you're saying there?
No, the alignment of the camera is actually quite good, because of this stereo camera, we can reconstruct the flight path of the camera much better than we can do on Earth. So we exactly know where the camera was at the time of image acquisition. That's another benefit of this camera. So that makes it, even if it's 20 years old, it makes it superior to all other cameras currently on Mars. Even, I mean, this camera has a pixel resolution of 12 meters or something, and the newer cameras have pixel resolutions of up to 30 centimeters. But they make high resolution images, but they really don't know where they are. And that's the purpose of our current project. Is, I don't have a picture of this now, but to take this newer high resolution camera and co-register it with our data automatically. So because our data is very precise in location. And then we get the problems that, of course, and then we use our image data for also image normalization. That means for getting rid of the seams and the different atmospheric contributions and stuff like that. So and you can clearly see when one image has a shadow here, the other image you adjust to that image will be dark in that area, even if it shouldn't be dark, probably because the sun was coming from another direction. So that's one demand for image for topographic normalization or shading removal or topographic correction, how it's called. And this I usually do with quite complex, or it's actually straightforward, but what I do is I calculate the DTM for every pixel, and I calculate the aspect and slope, and then I take the illumination angles and rotate them by aspect and slope. And then I multiply or divide actually the surface pixel by a synthetic surface, by some reflectance model. Yeah, and this way I can remove the shadow in very bad areas. Let's say it doesn't work so well. There is some overcorrection here. You can see it's very much it's very strong shadow here, and actually this should be more than, though it's really block shadow. Of course, then we get really problems. And yeah, it's never completely free of artifacts. Here you see some undulation like features. So of course you can introduce some filtering then to remove that. And there's always a degradation of resolution, but that is not so bad because as we use it only for normalization for other images, we can live with that degradation. But still, my idea for the project was then to create such unshadowed images by machine learning. So to feed the networks with paired images of the same location, because I have areas, we have natural images with no shadow, like when the sun is coming from a good direction, let's say, then if it's coming directly behind us, it's a problem because we have some photometric effects which makes the image look strange. But if it's, let's say, at 10 degrees or so from the normal surface normal, then it's perfect conditions, and I can look for images with 10 degrees and then check if there are other images on the same area with like 60 degrees sun incidence, which is bad. And this is what I have done, but I have not actually prepared.
Can I ask a question in the meantime?
Yeah. Go ahead.
Does this work?
I think you have to do it to turn off your microphone and use the one.
No, yeah, I was just curious about this model that you have been using before that accounts for reflectance that you told me about. So is that a package, or how do you correct for the shades currently exactly?
So there are different methods. One is, so you need a reflectance model. Yeah, the simplest reflectance model, which works already quite well, is the Lambertian model. It assumes like isochronous, how to say, equally distributed reflectance to all directions. So one other topic which comes into play is the bidirectional reflectance of the surface. So not all surfaces, of course, reflect in the same way. That's a major problem here. And but the Lambert model, which I have not here as an example, that has a big problem with higher illumination angles. So we get high illumination angles here, close to 90 degrees. And with the Lambert model, we get a strong overcorrection. But there are models like, it's called the Tellier model, or the C correction, which introduce some correcting factor. And another model I use is the Minard model. So that's a reflectance model, which is often used in remote sensing and in planetary remote sensing especially. And these, perform better and don't overcorrect. Because when you use the Lambert model, you would see these effects all the time. It's always then too strong, the correction effect. But if you want to do it really properly, then you would use physical models like the Hapke model. I mean, it's already easy on extraterrestrial planets because we don't have so much atmosphere, but the atmosphere of Mars is already strong enough to make everything very complicated. There are methods on asteroids where you can use these physical models, for example, on Vesta, but here on Mars, these don't work usually. Because then you would have to model the atmosphere as well, and you can't model the atmosphere from one image. You have to have several images of the same area from the same time to model the atmosphere. That's also done by other people. Sorry, I think I have only 20 minutes. I've not even started. Forgot to prepare one example I wanted to show. So now I have found these two images. The one on the bottom has an area where you clearly can see shadows. Yeah, they're not very strong, but at least you can see them. And the other one looks totally different. My opinion is that it looks so different because you can really see the surface features here and not the topography features. So it's from the same area, and this image is dominated by topography because it makes the most contribution to this image, the shading. It's not really shadow, but it's shading. And here you can see more surface features, and they're not very optimal because I think there's also some atmospheric contribution here. They have different values, so that's all not very because these are already reflectance values. But for a test and for this purpose, I think they are all right. So remember these images, one problem you can already see is that they don't have the same dimensions. And this is actually one problem which took me probably the longest times to get them get together. So what you can see here is the data structure. So these top of atmosphere images are the one you just see in the GIS. And then I have this other set of images which I have created from the DTM and from the pointing information. So for planetary purposes, because of this precise information of the location and the position and the orientation of the camera, we can calculate these angles. So that's, I can maybe, Antonio, you're interested in this. I can show you another time how I can do this, but it's really fascinating. For every pixel, I can calculate the sun incidence and the observer emission angle and the phase angle. That's the angle between them both. And as I have the DTM, this is this file, I can also calculate the aspect and slope. And from these, I rotate the illumination angles. So that's the incidence, emission, and phase. I can rotate them by aspect and slope. And so I get the illumination angles related to the surface pixel as it is oriented in the space. Yeah, not only to the ellipsoid of the planet, but to the real orientation of the surface pixel. And this allows me, in the traditional way I showed you before, to remove the shading. So this is what I had already, and my idea is that I create a paired data set, so with single patches, as we have seen it from this CNN example you all know. And for every patch, I have then one patch for the surface with shadow and one patch for the surface without shadow. So, and this was my idea. So first I had to create these patches. So I load in here all the images, and I create, so using GDAL, and I create an array with the dimensions of the images, which has 5 planes: the top of atmosphere, the incidence, the emission, the phase, and this glow is the global emission, the global incidence angle. So that's actually the incidence angle on the ellipsoid and not rotated by the surface. That's necessary for some models. And I thought maybe for the machine learning, it could be also a good predictor. And here you can see this has, I just added a couple of minutes ago. I normalized the values from 0 to 1 because the angles are in degree and the top of atmosphere is in reflectance. So it's not even 0 to 1. It's like you see it's 0.2 to 0.1, no, 0.02 in this case, and 0.1. So I normalized them to 0 to 1, I hope. But yeah, and here I check that the projections are the same and the geotransform form is the same. So that's not the whole geotransform, but just this is actually just the image scale. So it has to be the same, otherwise I would have to take care of that. And what I do here now is I calculate the extent of the both images and take for all the upper left X, Y, and lower right X, Y, I take the smallest extent. So this way I can make sure that I take only the overlapping area into account. I mean, in our example, the one image is completely contained in the other, but it could be different that there's only a partial overlap here. It would also work with this code. And then I change the image extents to this overlap area, and at the end I can see that they are now the same. And here I cut these extents. So image 1 cut, image 2 cut. Image 1 cut is actually the same as before because it's completely contained. No, sorry, image 2 cut is the one which is contained. And here you can see that I have now the areas cut, and one is with shadows and one is with less shadows, let's say. And here's the data structure. So I still have these 5 planes, and yeah, these images are quite large, actually 70,000 lines and 6,000 pixels. And from these large images, I now cut patches of 256 times 256. At first I had 28, but then after checking the methods, I realized that other people with these kind of methods more use larger patches, and it's even much better for really seeing the shadow and to check. I had to check if I really got the same area, because that was quite tricky. So I create these patches here. Yeah, at the end it looks quite simple, but of course the trick is always in the detail. The mean is in the, how do you say, the devil is in the detail. And but you can validate here that, for example, you can see, so these are now patches side by side, like with shadow, without shadow. And here you see a crater, and if you're if you have very good eyes, you can see it here. And this crater can be seen here. So I can be sure that this is the same area, and here's the same. We have this kind of ridge here, which is illuminated from the northeast, and here it's, and then you can already realize that you see completely different features when there's no shadow. Yeah, here you see some real albedo and not the shading. So here I make a stop and save these patches, so I don't have to create them all the time again. And here's another visualization of now like 10 of these patches, so they're all looking good in a way. I can make an example to plot here. If I want to plot the incidence, for example, this looks nice. I just change it to the other plane. And then this is the incidence of these patches. If I want to change it to the emission, and so on. But here you see that it looks like a slope image because it's rotated by slope. So that's a good sign. And here you can also see that in the unshadowed version, the emission angle is much stronger. That's because in this version, it's obviously taken from a side or so, but that's speculation now. So yeah, then this has to be set because it always crashed. It took me a long time to find this PyTorch CUDA memory trick to get around a problem, a bug or whatever, something which crashed the program. And then this part is the data preparation to get it into PyTorch. This is similar to the notebook from Antonio about the convolutional neural network I just showed before. And yeah, thanks to Antonio today, I managed to do this. He was a great help, and yeah, this would have probably I wouldn't have anything to show now if he wouldn't have helped me today. And yeah, there's a lot of stuff which is commented. And at the end, I have a data set. So that's the important point here, a torch compatible data set. So I converted this NumPy arrays into some torch tensor, I think it's called, or yeah. And here I set some variables. So the number of epochs, the starting epoch, the learning rate. I just took the ones from the example. Yeah, and actually now I have to come to the example. So I was Googling for things about shadow, how to do that, and I stumbled across this one. It's based on real shadow images. Actually, I don't have the publication here. And one thing I learned is that they first create a mask of the shadow. So they are considering real block shadow, not shading like in my case, but real block shadow. So they use like pictures with a photo camera and with a person standing in front of the sun or so, and you see the shadow of that person in that picture. And they are able to remove that with this method. But they use like a mask. So they first mask the shadow and then they remove it. So this was not very appropriate for my side, but they refer to another method where they don't use this mask thing, which is also available as code. So I tried to use this. And this is actually where I took the model code from. And I could have also written my data to this sort of structure, but they are using JPEG and it all doesn't fit because I have these 5 planes. But and that's why Antonio was such a great help to get my data into this model. And this is now the the initialization of all these objects we need for the network. So this is based on a method called cycle GAN. So I think Antonio has introduced GAN a little bit, like with 3 words.
Sebastian,
but, yeah.
Can you go back to the GitHub page for the cycle GAN, so we can illustrate a little bit of what the cycle GANs expect to do for you exactly?
Here?
Yeah, if you scroll down, I think we're going to show some examples with like natural images.
Ah, yeah, you're right. So yeah, they train horses and zebras, and then the algorithm is able to get fed by a horse image and create a zebra pattern on it, and the other way around, it creates a horse from a zebra. But it's doing much more. Even it can create winter images from summer images, or apples from oranges or stuff like that. So it's really crazy. I mean, what you can do with GAN is really a little bit scary, I think. For example, this is something which has been in the press, I think. So this guy Karas, who developed this algorithm, StyleGAN, he made a publication about creating fake faces. So he has a website, this person who does not exist, and they are creating fake faces from a collection of, they trained their algorithms on real faces, and every time you reload this page, they show a new face which from a person which doesn't exist, and you can't really see that this is not existing. So that's really frightening a little bit. Yeah, and I thought I can maybe make something like this with shadow removal. And yeah, so I tried.
So Sebastian, so in your case, this library is helping you to remove the shade.
No, this.
No.
Yeah, this library is to remove the shade. Yeah, you're right. I can show it to you. How can I get this publication? Or is that, no, that's a citation. No, maybe we have to, I think here it is. I mean, this is CycleGAN. Yeah, this is to create, like, to transfer some style of one image to another image. So they have not trained this network with paired data. That's the crazy thing about it. But the network is smart enough to, so you can make a photograph of flowers, and the algorithm can do like Monet style or Van Gogh style or Cézanne style out of these images. And actually, I think I didn't choose, because I'm working with this actually just 10 minutes before the presentation, because I'm really not completely understanding what I'm doing here. But I found out that it's probably not the right algorithm for me, because this is all working on unpaired data, and I have paired data, which should actually be simpler or more precise. So this is overkill, let's say. Yeah, it's overshooting my problem a little bit. So, but still, it's very interesting, I think. And I was thinking about to explain this GAN and CycleGAN stuff in this presentation, although I have already overrun my time. But I think, as I know exactly the same as you, and it doesn't make sense to read this in 5 minutes and then explain it to you. You can Google for what is GAN and what is CycleGAN, and then you can read it. But yeah, yeah, I really have to read into this to be able to understand it, and I'm not at all at this point. But yeah.
Yeah, let's just hold for 1 second. Did everyone understand what CycleGAN does? You understand the concept, right? Can you go back to the zebra horse example? Just like for one final run over it. It's just like, so you guys know what it does. So in case that you think you might have an application that benefits from it. Yeah, here is fine, I think. No, the GitHub, I think, is more clear because you have the GitHub there.
Was it here? No.
Yeah, all the way down. Yeah, the link in the
yeah.
bottom. Yeah, this one. Yeah. So basically what CycleGAN here is doing, you have data sets of zebras, right? Then the network tries to generalize what the zebra looks like, because they're going to show several images of zebras, right? So like at some point the network is going to abstract the concept zebra, which is like, it's an animal that sort of looks like a horse. Is it still muted? Yeah, okay. Sort of looks like a horse, but the difference is that it has stripes. So just like as he was explaining with the style transfer, okay, what you're gonna do is next is like, if I have a horse and I say that I wanna assign attributes of a zebra to it, the CycleGAN is able to do that for you. So it adds attributes from a zebra, which like the network learned how to abstract the idea of zebra to something that had similar features, which like the horse shape, to the horse, right? So now you give stripes to a horse. In the same way how you do that, you could, for example, add like features to someone's face, which is basically what they do in that example that Sebastian was showing earlier, which like small modifications in the face, but realistic, because those are still features that generalize to someone's face. Okay, so that's a really powerful method for like augmenting your data sets. For example, some of you had issues with like very small data sets. When they are imaging, you can still generate really realistic images, and those are really powerful augmentation techniques in general. Okay, thank you, Sebastian. Keep going.
Yeah, there was one interesting art project I found while searching for it. So they have a data set with a training network. They have a network which they trained with only with mountains, and then there was a camera at this art exhibition, and the network was then converting all the people's figures, or how do you say, the outlines or the shapes of the persons into mountains, because the network was only aware of mountains somehow. So that was really funny. So you can really influence the result by what you give as a training, of course. Okay, and in general, the GAN works like that. You have a generator, so that generates images, and then you have a discriminator, which decides if the image is good or not. So that's the general idea about GAN. And this cycle GAN does even more. And what I found out while reading for it, it actually, the benefit of it is that you don't need these paired data sets. So it can learn even from unpaired data sets. And so that is, on the one hand side, it doesn't fit to my problem, because I have this highly I put so much work in creating these data sets and the paired data sets. But on the other hand, I can just use any images with no shadow then, and any other images with shadow, and because the problem is always that we don't have enough images for training or the networks. And this makes it much easier for me to create a training data set. So I just used the wrong data set for this training, but I can use the same cycle GAN for unpaired data sets, which are much easier to provide. So that doesn't really fit to this thing, but so at the end it makes it very useful. So this code is just taken from this GitHub repository here. So I have not taken everything and adapted it to my need, again with the help of Antonio. Thank you very much. And now it worked out. So the problematic thing is the data loader here. And yeah, then what this software also uses is a tool called Wisdom, and you have to create a Wisdom server on the terminal, and then it visualizes. So it's running here. It visualizes the logging of the modeling and the training. And yeah, we had some problem. What I actually do, I haven't said that. For simplicity and for starting, I have changed my data then from these 5 planes to just use 1 plane. So I reduced my data here, I currently don't use the incidence, emission, and all these angles, and I just use the image because it's more related to what they are doing, and I think the network should definitely work with that, even if it's probably not using all information I have, but it should, for a test, it should be a good starting point. So this is why you see the 1 here, and that's why I had to juggle around with it here, because it was complaining that the sizes don't match. And this is again taken from this GitHub repo. So this is now the training loop. You see there are not a lot of nodes and layers involved, and these are actually these GAN things. So they have a real A and a real B and a fake A and a fake B, and then something is going on to check them against each other. And yeah, that's what's going on. And then they try to minimize this.
Sebastian,
Yeah.
Yeah, maybe just to explain what this real and fake stands for. So the idea of the GAN in general, right? GANs in the first place stands for generative adversarial networks. And why are they adversarial? So you have basically two networks, okay? And one network is responsible for just generating realistic images. So like initially, of course, the network has no idea what a realistic image looks like. So the network is just trying to generate the image. And on the other side, you have a network that's called the discriminator. So like a network that's only trying to differentiate between images that were fabricated, right, by the generator from real image. So what's the end goal? During this adversarial training, you have a discriminator that's trying to tell apart like what's coming from the generator from real image. And the discriminator is getting also better in trying to separate this fake from real, okay? So when this training goes on for a very long time, you have a discriminator that's basically not possible of differentiating if the image is fabricated or actually real. And when you get to that point, that means that the generator is really good. Because if the discriminator can no longer tell apart fake from real, that's when you get super realistic images. You see? So when you see fake there, that means that that's a sample that's coming from the generator, right? And when you see real, that means that's a sample that's coming from the actual data set. So that's an actual patch of a Mars image, okay? And yeah, I think that's enough details. Yeah, okay, yeah. Please go on.
Yeah, Sebastian, try to summarize that we have also another presentation.
Yeah, so yeah, that's, and then there's another piece of code which I have to run. It's then the test, but I have not come so far to let it run. I can just show you the effect of what the training looks like. So here I now started it, and you see it's going in the you see here the steps and the epoch, and then you can see this visualization here, and it starts to compare the real image. So it creates fake images and starts this comparing, and you see that it builds up. But I also realized that it's taking a long time to run. So I have a GPU actually, and it yeah, I think I have to let it run for some days to get a result.
You notice that now you have two losses there, right?
Yeah, it's
yeah.
There's several losses.
Yeah, go ahead.
No, tell me.
No, yeah, what I was going to say is that like now you have two losses because you have two networks being trained in parallel, right? The generator and the discriminator that is being trained.
Yeah. And then there's, and because it's a cycle GAN, it's even more complex.
Right. Cool.
But this visualization is quite nice. So you can really, because now this looks much better. In the beginning, it looked really weird. And I could just, with this visualization, I could see that the network is doing something right.
The first panel on the top left is the real.
Yeah, here it's called real A and real B. So it must be one with shadow and but I don't know why there is real A. No, actually, no, okay, no. Yeah, as I said, I use a paired data set, which is not appropriate here. There should be like, you can imagine real A should be the horse and real B should be the zebra.
Right.
So yeah, it's still right. So real A is without shadow, real B is with shadow. No, opposite. Real A is with shadow and real B is without shadow. And then there are the two fakes and they are checked against each other. But they don't have to be necessarily from the same area.
Yeah. But you can already see that it's capturing some of the patterns from the original.
Yeah, you're right.
Yeah, so it's learning something for sure. Cool.
I don't know why this has these interpolation artifacts in here, and it looks like a little bit like saturation.
Yeah, I mean that's something that might go away with training. You see that the loss curves are still going down, right? So it might get better over time.
Yeah, it slows down my computer completely, so something must go on there.
Yeah.
But now that I have the code, I can also put it on our cluster. We have a university cluster, and then I can leave it there for a couple of weeks.
Okay, thank you, Sebastian. So far, which one was the most difficult part in your coding procedure? Probably
It's hard to say.
understand
So the most difficult part was actually the data preparation. So creating these patches, but it
Yeah.
was also straightforward because I know what I do. The other part was, then try and error to get it running, but I'm using existing code, which I have no clue what I'm doing. So this was not as hard, but it's also, but if I would have to understand what I'm doing, it's much harder. And then I had help from Antonio. That's why it wasn't that hard. Otherwise, it would have taken me much more time if I wouldn't have given up, I would say. So actually, yeah.
Okay, thank you. Any other question for Sebastian? Okay, perfect, Sebastian. So send me your Jupyter notebook. If you need to finish, you can finish even tomorrow is fine. And also the PDF. So I will put all of them in the spatial ecology website.